expression, I will substitute k equal to 3. This becomes independent of k. This is anyways independent of k. This is k equal to 3. When this is 3, it becomes 2 into 3, that is 6. And this is 3. This is turning up to be 9. So 3 into 3. So I shall write that expression as w4 raised to 0 plus w4 raised to 3 into 2 plus w4 raised to 2 into 3, that is 6, plus 3 into w4 raised to 3 into 3, that is 9. The values are, some of the values are known to us, like w4 raised to 0 is 1, we have already shown that, plus 2 into w4 raised to 3. So what was the value of w4 raised to 3? We have determined the value. w4 raised to 3 happened to be j. So I can substitute that value here, 2 into j, plus w4 raised to 6 is written over here. w4 raised to 6 was determined using this process, and we got it as minus 1, plus 3 into, only value that is not known to us right now is w4 raised to 9. How do we calculate w4 raised to 9? w4 raised to 9 is e raised to minus j 2 pi by 4 into 9. So this is e raised to minus j 2, we can write it as it should have been 18 pi by 4. So this is cos of 18 pi by 4 minus j sine 18 pi by 4. Okay, so in your you can use your calculator, set it up in radians mode, and find the value 18 pi by 4. So the value happens to be 0 minus j sine 18 pi by 4, which is 1. So this value is minus j. Okay, so we got the value as w4 raised to 9 is minus j. So when you simplify this thing, you get plus 1 and minus 1 getting cancelled. So you have 2j minus 3j, which is minus j. Okay, let us summarize all the values that we have got. That is x of k equal to, we will write x of 0 here, we will write x of 1 here, x of 2 here, and x of 3 here. Okay, so what is x of 0? Let's go back and see the expression. So x of 0 is 7, x of 1 is j, x of 2 is minus 3 here. Okay, and x of 4 we have x of 3, yeah, x of 3 is minus j. So we will write each of these values, 7 j minus 3 minus j. So this is the discrete Fourier transform of the signal x of a. That is, if we have the signal like 1 2 1 3, this is what is the signal on which we were working till now. So if you take the discrete Fourier transform of that, we will get it as 7 j minus 3 and minus j. So this is the discrete Fourier transform. So from time domain, we transformed it into frequency domain representation. That is, again I am taking you back to my representation of this signal. So what it means is, the Fourier transform that line shown in red is a continuous waveform, and I am taking 4 samples, one here, one here, one here, and one happened to be over here. So the magnitude only is shown over here. So the values happens to be like 7, then you have j, then minus 3 and minus j. So the 4 samples have been taken. So 4-point DFT of a signal. Now I want you to note down the twiddle factors at the last page of your notebook, so that you can turn the page and you can observe the twiddle factors as a ready reckoner. I also want you to observe these interesting facts about this twiddle factor. So twiddle factor is say represented on a complex plane. So this is a real part, this is a negative real tilt, say this is imaginary and this is minus imaginary. So this is the origin. Okay, where is W4 raised to 0. So W4 raised to 0 happens to be at point 1, right? So on the complex plane, suppose 1 is over here. So this is W4 raised to 0. W4 raised to 0. Similarly, where is W4 raised to 1? W4 raised to 1 is minus j. So minus j is over here. So I can write it as 1. This is minus j. So this value is W4 raised to 1. So 0 and 1. W4 raised to 1. Similarly, where is W4 raised to 2? W4 raised to 2 is at minus 1. So where is minus 1? So this is the real axis. So it should be minus 1 is over here. So this the value is W4 raised to 2. And similarly, W4 raised to 3 is at plus j. So W4 raised to 3. So if you have observed while plotting the W4 raised to 0, 1, 2, 3. On the same line, we also determined W4 raised to 4. W4 raised to 4 happens to be equal to 1. So W4 raised to 4 is over here. So apart from this, it is W4 raised to 4. So 0, 1, 2, 3, 4. So can you guess where will W4 raised to 5? So it should be over here. So if you want, W4 raised to 5 is e raised to minus j 2 pi by 4 into 5. So it is e raised to minus j 10 pi by 4. You can plot it and observe that the value will be minus j. Okay, so W4 raised to 0, W4 raised to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. So this clockwise movement, clockwise rotation of the twiddle factors can be observed. So the twiddle factor values, there are for n equal to 4, there are only 4 values of the twiddle factor. One is plus 1, minus 1, plus j and minus j. These are the only twiddle factors, whether it is the expression as shown here, W4 is to 0, W4 is to 3, W4 is to 6 or W4 is to 9 or any other such values. There are going to be only 4 values of the twiddle factor. We will be using continuously only these 4 values when n is 4. That means when the question says obtain 4-point DFT, the twiddle factors that are going to be used are a repetition of 1, 1, minus j, minus 1 and plus j. So this rotation keeps happening. So this is our one of the numerical. So I encourage you to take up other signals. So you can try the Fourier transform of the following signals x of n. Obtain the 4-point DFT. The question can be obtain the 4-point DFT of the following signals. X of n is say 3, minus 2, 1, 6. Try out the Fourier transform of this. X of n equal to Fourier transform of 1, 1, 1 and 1. Okay, so each of this will give you some very interesting Fourier transforms, and you get acquainted with the method to solve. So once you are knowing how to calculate the Fourier transform, the twiddle factors need not be individually calculated. So you can mentally map the Fourier transform. So you can write this representation and begin the W4 raised to 0 over here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and so on. So this representation becomes easy for you to effectively and efficiently calculate the discrete Fourier transform. So this is the example for 4-point DFT. Let us try to calculate or obtain the 5-point DFT of a signal. Say the question can be something like this: obtain the 5-point DFT of x of n. What is the signal? Say it is 2, 3, 1, minus 1. 2, 3, 1, minus 1. Some very important and observations are to be done. What is the length of the signal? Length of the signal happens to be only 4 samples. Therefore, length is 4. What is the length of the DFT that has been asked? So here n is being given as 5. That is, you have to obtain 5-point DFT. What does it mean? So again, let us plot that Fourier transform. So Fourier, this can be one cycle. So that's this way. It continues. So suppose if this is one period, that is x of omega, we will be now taking 5 samples in this range. So one here, second, third, fourth, and fifth. So we will be taking 5 samples. One is here. So these are the samples that you have to take at k equal to 0, 1, 2, 3, and 4. So the Fourier transform is a continuous signal. Fourier transform happens to be continuous, but out of that continuous Fourier transform, I want to take only 5 samples. So the question says obtain 5-point DFT. We already know the formula of Fourier transform, that is x of k equal to summation x of n w n raised to kn, n is equal to 0 to n minus 1. So if I were to substitute n in this expression, it will be x of n w 5 raised to kn. N is equal to 0 to n minus 1. N is capital N is 5. That means you have been asked to obtain 5-point DFT. Therefore, n is 5. So 5 minus 1 will be 4. So let us expand this. It will be x of 0 w5 raised to kn, k into n, n is 0, plus x of 1 w5 raised to k into 1, plus x of 1 w5 raised to k into 2, plus x of 3 w5 raised to k into 3, plus x of 4 w5 raised to k into 4. What is the next term? Plus x of 5 w5 raised to k into 5. No, that is not needed because n is ranging only from 0 to 4. N is equal to 0, 1, so this should have been 2, 2, 3, and 4. So it goes only up to x of 4. Now let us substitute the values. So what is x of 0? X of 0 is 2. So 2 into w5 raised to k into 0 is anyway 0, plus x of 1 is 3 w5 raised to k into 1, plus x of 2 is 1 into w5 raised to 2k, plus x of 3 is minus 1 w5 raised to 3k, plus you observe what is x of 4, right? So x of 4 here, x of 4 is fourth element. So this is x of 0, x of 1, x of 2, x of 3, x of 4. There is no x of 4. So this value itself is 0. So I can write it as 0 into w 5 raised to k into 4 anyways happens to be 0. So I'll just end it up with 0 over here. So this is the expression x of k. Okay, so you can box this element. This is our defining equation. So x of k is equal to 2 into w5 raised to 0 plus 3 into w5 raised to k plus 1 into w5 raised to 2k. The 1 into w5 raised to 2k can be written still as w5 raised to 2k minus w5 raised to 3k. Lastly, you have plus 0 that can be neglected. Now, what is the range of k? In this expression, k ranges from 0 to n minus 1. That is 0 to n is 5. Therefore, 5 minus 1 is 4. So, n is 0 to 4. So, what we need to do now is evaluate each of these expression. For example, for k equal to 0. For k equal to 0, x of 0 is 2 into w5 raised to 0 plus 3 into, in this expression I will put w5 raised to 0 plus 1 into w5 raised to 2k. 2k is 2 into 0 like that. So w5 raised to 3 into 0 which is again 0. So we will write it as these are the values. So now we are again facing the same situation as the previous example. So previous example we had determined the wn raised to kn values, right? So wn raised to kn we determined that as e raised to minus j 2 pi by n kn. So we went on evaluating for n being 4. By chance, if we had n equal to 4 in this expression, we could have used the same the same twiddle factor values, but now it is w5 raised to kn. So we need to first evaluate all the values of w5 raised to k, and formula is still the same. That is w5 raised to 0 is e raised to minus j 2 pi by 5 into 0, which is e raised to minus j 0, which is equal to 1. That is cos of, we can write it as cos of 0 minus j sine of 0. So that value is 1. Similarly, what is w5 raised to 1? So w5 raised to 1 is e raised to minus j 2 pi by 5 into 1. That is cos of 2 pi by 5 minus j sine 2 pi by 5. Okay, so you can use your calculator, put your calculator always in this radians mode and find out cos of 2 pi by 5. Cos of 2 pi by 5 happens to be 0.309 minus j sine. So you can write it as sine of 2 pi by 5, which is 0.951. 0.951. So the twiddle factor value is w5 raised to 1 is 0.309 minus j 0.951. On the same line, you can write down w5 raised to 2. Yeah, I'll give you the values so you can quicken up the calculation. So w5 raised to 2 happens to be 0.809 minus j 0.5877 w5 raised to 2. Then w5 raised to 3 value is minus 0.809 plus j 5877. So this is the value. Then w5 raised to 4 is 0.309 plus j 0.951. So these are the values. So let us quickly plot these values on the complex plane. Where is W 5 raised to 0, 1, 2, 3 and so on. So let's see here, this is the real part, this is the negative real axis, this is imaginary axis, this is negative. So where is W5 raised to 0? W5 raised to 0 is 1 over here, W5 raised to 0. This is 1, W5 raised to 0. Similarly, W5 raised to 1, W5 raised to 1 is 0.309 minus 0.95. So, the real part is 0.309 and imaginary part is negative 0.951. So, somewhere, I can draw it over here, approximately. So, approximately I can try it over here, this way. And similarly, so this is W5 raised to 0, this is W5 raised to 1. You will soon realize that there is some pattern in these representation. Okay, the W5 raised to 2, where is it? It is minus 0.809 and minus J 0.5877. So minus 0.809 happens to be somewhere here and the negative value over here. This is an approximate representation I am doing. So W5 raised to 2. On the same line, W5 raised to 3 will be, you can observe the W5 raised to 2 and 3, they are all conjugate pair, right? So negative value happens to be same, sorry, the imaginary values are conjugate of each other. So if I were to draw it on the same line, this will be W5 raised to 3. Reason, here the value is same, that is minus 0.89 and this is plus J 0.588. Okay, and finally I have this complex conjugate of W5 raised to 1. So it will be somewhere over here. So this is W5 raised to 4. So if you have already observed keenly, then all these values, right, are lying on a circle. They are lying on a circle of radius 1. Okay, so they are all lying, all these points are lying on a circle of radius 1. So these are the twiddle factors. So W5 raised to 0, 1, 2, 3, 4. Similarly, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 and so on. So this clockwise rotation of these twiddle factor keeps happening. So these twiddle factors are independent of which signal you are referring to. Like x of n, in this case it happens to be 2, 3, 1 and minus 1. Suppose instead of 2, 3, 1 minus 1, if you have 5, 3, 1 minus 1, or suppose you have 8, 6, 1 minus 1, or 1 minus 1 and 1 minus 1, no matter what signal it is, the 5-point twiddle factors will always be like this. So you are encouraged to find out these twiddle factors and note them down in the last page, plot them in the last page of your notebook, so that whenever you are solving these examples, you can look into those as a ready reckoner and then solve the examples more efficiently. Okay, so let's come back to solving these this example. So k equal to 0 we have taken. X of 0 is 2 into W5 raised to 0 plus 3 into W5 raised to 0 and so on. So let us substitute these values. So this is 2 into W5 raised to 0. What is the value of W5 raised to 0? This happens to be 1. So 2 into 1 plus 3 into 1 plus 1 minus 1, because all are W5 raised to 0. So this is 2 plus 3, 1 minus 1 is 0. So 2 plus 3 is 5. Okay, so x of 0 value, that is first sample over here, the first sample of this x of j omega happens to be 5. So this is the value. Similarly, we can take up for k equal to, for k is equal to 1, we can find out x of 1 is equal to, from the boxed expression here, it is w5 raised to 0 plus 3 into w5 raised to 1 plus 1 into w5 raised to 2k, which is just 2, minus w5 raised to 3k. 3 into k is 3. Okay, so substitute the values. So 2 into w5 raised to 0 is 1, so 2 into 1 is 2, so I'll write just at 2 plus 3 into, you see w5 raised to 1, w5 raised to 1 over here, right? So this value is 0.309 minus j 0.951, okay, plus w5 raised to 2, w5 raised to 2 is minus 0.809 minus j 0.5877. This is w5 raised to 2 minus w5 raised to 3. w5 raised to 3 is minus 0.809 plus j 0.5877. Okay, so you can simplify this. So this is 2 plus 3 into 0.309 minus j 0.951 minus 0.809 minus j 0.5877, minus of minus is plus 0.809, minus of this is minus j 0.5877. So you will see here, this is getting cancelled and these two are same values. So let's use a calculator and find out the values. The value is 2.927 minus j 4.0284. So this is x of 1. This is x of 1. That means the second value in our 5-point signal, this happens to be x of 1. On the same line, I will be able to tell you the next values. The other values, that is x of 1 and x of 2 we could determine, x of 3 and x of 4 are also like this. So all this are to be determined using this boxed expression only, expression say a. So using a, we have to expand for different value of k. So I have shown it for k equal to 1 and k equal to 0 and 1. For k equal to 2 also it can be determined. One property of the DFT is that if the signal, input signal, that is x of n, is a real signal, the one that we have considered is a real signal because all the values are real over here, like 2, 3, 1, minus 1. We don't have any signal like 2, 3j, 1 plus 6j, minus 1, minus 2, and so on, right? So we have all the values, all the samples that are there in this signal are all real. So such signals are called real signal. In case the signal is real, then there is a symmetry in the DFT. I want you to take a relook into the DFT that we obtained for the 4-point sample previously, right? So the 4-point sample that we have the signal that was there, it gave us a DFT like x of k equal to 7 j minus 3 and minus j. Okay, so this is our x of 0, this is x of 1, this is x of 2, and this is x of 3. You look at the n. What was n? N was equal to 4. Therefore, what is n by 2? That happens to be half point. So x of 2 is this value, correct? So this is the midpoint of the x of k. The values over here, they will be complex conjugate. Okay, by chance we had the previous signal, the value is j, the other value over here is just complex conjugate of that value, so it is minus j. On the same line, the 5-point DFT that we have determined now here, you can observe the midpoint happens to be this is 5, right? So midpoint is 5 by 2, that is 2.5. So where is 2.5? The x of 2 is here and x of 3 is here. So x of 2 will be somewhere over here. Okay, so this is the midpoint. So across midpoint, so these two values will be complex conjugate. These two values will be complex conjugate of one another. Okay, so you can, on that line, you can quickly determine. So you don't have to calculate all the values of the DFT, like from starting from k equal to 0 till k equal to 4. If you were to just determine x of 0, x of 1 and x of 2, then directly you can write what is x of 3 and x of 4. The x of 2 is complex conjugate of x of 3 or vice versa, and 1 and 4 are also conjugate of each other. So if you have determined 1, you can determine 4. If you have determined 2, you can determine 3. So that way the calculation can be, the speed can be increased. Okay, so this is our solution. In further sections, we shall also try to take the 5-point DFT, 6-point DFT, and so on. Thank you.